Okay. Hi guys. Good morning.
Good morning, sir.
Ah, okay. Fine. So we will continue. So we saw last class what are the three types of velocities, and most importantly, we saw this Maxwell's distribution curves, right? So I told you we got to the introduction of what is this most probable velocity, VMT or UMT, most probable velocity, right? Okay. So then we did some problems on that, right? Okay. So that's what we saw. So this is about the three formulas. That's it. Okay. So today also we are going to deal something related to the movement of gases only, right? So last class we since we spoke about velocity, right? So here also it is somewhere related to the same concept, right? So we're going to speak about the movement in some way, right? So there is going to be one phenomenon which I want to speak about, right? So we already know this phenomenon, but anyways we'll see it again. So we are going to see this diffusion or effusion process. Okay, we are going to see this diffusion or effusion process, right? Okay, so generally, how will you define diffusion, people? How will you define diffusion? Effusion we'll see later. Tell me what is diffusion. Nobody knows what is diffusion.
When one substance, when a solute dissolves in a solvent, we say it's diffused.
Solid dissolved in a solvent. No, it's that is called dissolution, right? What is diffusion? So basically, please understand. Let me give you a very small example, right? Say someone, your mom is cooking in the kitchen, something very good, right? Say you are in the hall, right? So what happens? The good smell reaches you, right? You're able to smell the good aroma, like because it reaches your nose from the kitchen, isn't it? Right? So what is happening there? Basically, the gas particles are moving through the air, or whatever the smell, the aroma particles are moving through the air, and they're reaching your nose, isn't it? Right? So this movement of gases is what is called as your diffusion, right? Or if I have to put it in a very solid definition, right? So this is how I can put it. So it is the movement of substance, right, from a region of higher concentration, right? Okay, take down the definition, please. Please take down the definition of diffusion. It is the movement of particles. It is the movement of particles, or you write the heading as diffusion of gases, right? Write the heading as diffusion of gases, so that we'll be able to give you a little bit more insight in the definition, right? So diffusion of gases. So it is the movement of gaseous particles. The definition says it is the movement of gaseous particles, right, from a region of high partial pressure, from a region of high partial pressure to the region of lower partial pressure, to the region of lower partial pressure, right? Very simple definition. So obviously inside the kitchen, right, where that is where she's cooking, right? So obviously that place I'll have very high concentration or high partial pressure of that particular smell. But near you, there would definitely be lesser, like say almost no traces of that smell. So what happens? from the region of higher partial pressure, it is going to reach your nose, where basically you have lesser partial pressure of that smell. So that movement is what is called as your diffusion. Very as simple as that, right? Or if at all I want to give you another example, say I can give you an example like this. Say I have closed container like this with a partition, right? Say in this side I have say O2 gas, right? And say this side I have N2 gas, right? Okay. So now if I take down this, right? If I take down this, is it going to stay like this? Is it going to
No,
stay like
sir.
this only? Even if
It'll mix.
obviously they will mix, right? So they I'll be getting a situation like this, right? Something like this. O2 and N2 gases are mixing. Again, obviously, I have to make sure that they're not reacting, right? That I have to make sure. If they are reacting, again, that will go to some other cases, but making sure they don't react, right? So this is what happens. So now how will I talk about, give the definition here? So now I have two gases, right? So I have to talk for diffusion in terms of two different gases. Say, for example, if I say that O2 is here in this place, the O2's concentration is high, right? So the moment this is open, right? So the O2 molecule, it is going to move to a side where it has lesser partial pressure, that is this side. So it is going to move from here to here. Same way goes with N2. Here I have high partial pressure. It is going to move to a region where I have lesser partial pressure, that is this side. So eventually they will mix, right? So this again, this process is what is called as diffusion. Very, very simple, right? So diffusion is basically movement of gaseous particles from the region of lower concentration to the region of lesser or lower, higher concentration to the region of lower concentration, right? Fine. Okay, this is not we are going to study, right? So what we are going to study is, right, how to put it. Say if I have two different gases, right? Say let me put it like this. Okay. Uh, uh, okay. Or okay, put it like this. Cool. So right, say I have five benches or five chairs. People are sitting. Okay, there are five chairs. People are sitting. Okay, right. Say this side I have say helium gas. Helium. Okay, fine. This side I have helium gas coming. Okay, and say from that side I have oxygen gas coming. Okay, right. I have helium gas coming from this side. I have oxygen gas coming from that side. Right. Now the thing is, if I ask you, where will they meet? Where will, in the sense, which say this is 1 2 3 4 5, if I mark it, right, 1 2 3 4 5, if I mark it, right, where will they meet? What will be your answer?
Third.
Third. Okay, fine. Do you have any explanation for that, or it's my guess?
Yes, sir.
Okay, fine. Any other guesses? Right. So one guy says they are going to meet at 3. Any other? You can either yes, say it is going to be 3, or you can deny it and say give some other answer.
So where it means, does it depend on the speed of the gas particle? Its mass velocity.
Exactly. So that's what I'm trying to tell here, right? So yeah, it actually depends. Okay, fine. It is going to depend on that. Tell me, what is your notion? Where are they going to meet? I will definitely speak about all those things. Yes.
Around 4, sir. 3 or 4.
Around 4. Okay, makes sense. Right. So anyways, we'll see. Right. So the answer to this question is definitely they are they are not going to meet at the center point. No, right? So they're going to definitely meet either towards that side or towards this side. Like that's how it is going to be. Okay. So why? Okay. Now is the thing we are going to speak. Now this is also diffusion, right? The process of diffusion. The gas particles are moving from one side to another side, right? Okay. So now we are going to speak about this rate of diffusion, right? So if I have two gases, right? If I have two gases, right? Say I want to compare which gas will move fast or which gas will diffuse faster, and which gas will not will diffuse a little slower, right? So how are we going to compare this, right? So in this case, I'm going to tell you that actually we are going to meet. I mean, these two gases are going to meet near 4, I would say, right? Now, if I tell you this, what are you understanding from this? You tell me. I'm saying that helium and oxygen are going to meet at 4 means
Helium possesses a greater kinetic energy than oxygen.
okay. So that means helium is diffusing faster. Can I put it that way? Since we're speaking
Yes,
about
sir.
diffusion, right? Okay. So as yeah, kinetic energy, obviously, right? So the thing is, if I'm saying that in this case they are meeting at 4, right? So for what you see, oxygen has moved only one place, that is from 5 to 4, right? But look at helium. Helium has moved from 1 to 4. The distance traveled by helium is greater, but at the same time, right? We're talking about when they're going to meet. Say at time t is equal to 0, I let both of them outside, both of them this side and that side, right? But still, they are meeting at 4, indicating that helium is diffusing faster than oxygen, right? Okay. Now, how did we know all this? How to compare all this, right? So again, there is a law which is going to help us, right? There is a law which was stated by Mr. Graham, or I would say Dr. Graham, not a Graham Bell, no, right? So I'm a scientist, right? So he gave a law by which I'll be able to compare, right? What will be the rate of diffusions of different gases, right? Please take down the statement. We are going to see. Oh, 1 second. There's my duster. Only I had it right. Here. Yes. So here we are going to see Graham's law of. Actually, wait. Before saying this, don't take this down. 1 second. I'll tell you what is effusion also. So the law is common for both of them, right? Anyways, you can just take down. Like I'm going to see, right, Graham's law of diffusion or effusion. Like, see, this diffusion or effusion of almost same only, but still, there's a small difference when it comes to effusion, right? So we'll see what is effusion first. Then we'll go for the rate of effusion or rate of diffusion, right? Okay. I'd say like assume this, okay? So what is effusion is, say you have a balloon with you. You have a bloated balloon, that is, you have given air, it is a little big, okay, right? So what I do is I very slowly taking a pin, right, and I'm making a very small hole in the balloon. Again, you have to be very careful that you are not bursting the balloon. You have to do it very slowly. Okay, fine. Anyways, so what I'm going to do, I have a balloon, right? So I'm making a very small hole into the balloon, making sure that the balloon is not bursting. Like that is the condition. You can, just to make you understand what effusion is, right? So I'm going to make a hole. Okay, now what is going to happen, right? So obviously through that hole, through that small hole you made, right, the gases are going to come out, isn't it? Right? The gases are going to come out through that small hole, right? This phenomena is what is called as your effusion, right? So how do I properly put it, right? Effusion is diffusion through a small hole, as simple as that. Did you get it? Right? Effusion is diffusion. Obviously, the gas particles are moving, no doubt. Again, from a region of from a region of higher partial pressure to the region of lower partial pressure. Yes, but the only difference is, right, here it is happening through a small hole, right? That is effusion. So effusion is diffusion happening through a small hole. That's what is effusion. Okay, right? So hope everybody understood what is effusion and diffusion, right? So anyways, like whatever it is, the speed of the gas, I mean the rate of diffusion or effusion is going to depend upon this law only. Okay, so now take down what is this law. Graham's law of diffusion or effusion. Take down. Right. So it's the rate of diffusion or effusion. The rate of diffusion or effusion is inversely proportional to the square root. Oh, what did I say? I said the rate of diffusion or effusion of a gas, please include that. The rate of diffusion or effusion of a gas is inversely proportional to its square root of inversely proportional to its square root of molar mass, to its square root of molar mass, right? Okay, so now if I repeat the statement, right, so the rate of diffusion or effusion, right, the rate of diffusion or effusion of a gas is inversely proportional to the square root of its molecular mass or molar mass, right? So very obviously, right? So look at the statement. What it says mathematically, if I write this, the rate of diffusion R, if I keep it as R, right, will be will be inversely proportional to the root of molecular mass. That's what they say, right? That's what your statement says, right? The rate of diffusion of a gas or effusion of a gas is inversely proportional to its square root of its molecular mass, right? So mathematically, this is how I write it, right? And this makes logical sense also, right? Right? Obviously, if I have very how to put it, if again say a person who's lean and a person who's little stout, right? Obviously, a person who's lean will move faster, right? So again, that makes sense. The higher the mass, difficult to move. Lower the mass, easy to move. So that's what Graham's law says, right? R is inversely proportional, inversely related to the root of m, right? So obviously now, if I can put a constant, right, I'll be able to write it as R is equal to K by root m, but that we are not interested in, right? We are not going to find the actual rate. Yeah, maybe sometime problems we will find, but not so much. Right? I'll tell you how to find also. Don't worry, right? But not with this exactly. With this, we will be able to compare two gases' rate of diffusion, right? Say we compared here, right? Helium and oxygen, right? So I can even tell that here helium moves 4 times faster than oxygen, because oxygen moved only 1 block, helium moved 4 blocks, right? So what is the ratio? 1:4. So helium moves 4 times faster than O2. So that, like that kind of stuff we'll be able to do. How many times faster a particular gas diffuses more than some other gas? All these kind of correlations will be able to make, right? How Very, very simple. I can rewrite this equation for two gases as R1 by R2, that is rate of diffusion of first gas divided by rate of diffusion of second gas. I'll be able to write this as a root of M2 by M1. Right? M2 is the molecular mass of the second gas divided by molecular mass of the first gas. Okay, right? So R1 by R2 is equal to root of M2 by M1. Root of M2 by M1. Cool, right? So that is about Graham's law. Okay, that is about Graham's law. Right. Now the next question is, sir, does this obviously please understand that the conditions, other conditions, that is the pressure, right? The pressure in the sense the external, the external pressure, right? The temperature, right? What else? Now density of the gas, right? All these also actually plays a role in deciding the rate of diffusion, right? Definitely, particularly if I speak about effusion, right? If I speak about effusion, let me put it this way. Okay, let me give you a situation, then you'll be able to understand. Right. Say I have a vessel, right? I have a vessel in this. I have a gas. Now assume that the gas inside is having a pressure of say 2 atm, right? And I'm making a very small hole here. Okay, fine. I'll give you another situation. Same volume, everything is same temperature, everything is same gas also, right? And again, I'm making a very small hole and assume that the size of the hole here, the size of the hole here is again same. The only difference I'm having is that here I'm having 3 atm pressure. The gas here is having a pressure of 3 atm. Now, say if I say this as condition, situation 1 and situation 2, you tell me in which situation effusion occurs faster. In which situation? Obviously, this is effusion, right? Diffusion of a gas through a small hole. Yes? Okay. So I'm asking in which situation effusion occurs faster?
Two ATM.
Any reasons? No reasons. Okay. Anybody wants to give on like say contradict or say support his answer? Anybody? There are good. There is good strength here. So nobody wants to support or nobody wants to object. Rohan says it is, sir, it is first case. That's where it is moving faster, or effusion, the rate of effusion is faster there. Is there anybody who's going to support it or say no, it's going to be 3? At least make a guess. I'm not going to ask you why is it happening. If you tell me why, well and good for your answer. Okay. All of you unmute yourself. I'm just going to take a vote. How many of you say that it is first case? Rate of effusion is faster in first case. Just tell me yes. 1.
First case, sir.
Okay. 2.
First case, sir.
First
3,
case, sir.
4. Okay, fine. So rest all of you are saying. So almost I would say second case. How many of you are voting for it?
Sir, second case.
1.
The second case.
Okay. 2.
Second case, sir.
Okay. 3. Okay, I think that's it. 1, 2, 3, 4, 5, 6, 7, 8. One more. One more guy didn't even vote. 1, 2, 3,
Sir, I'm
4, 1, 2,
thinking,
3.
sir.
You're thinking. Okay, fine. So we'll have we'll have a neutral person also then, right? So So we have equal votes, right? So my answer matters right now, right? Obviously, 3-3 we got. And obviously, I'm going to tell you the correct answer. Right? The correct answer is 380. Second case. Fine. So anybody wants to give me a reason, an explanation for this? Shruti, you want to give one? You told it is second case.
Sir, I think because it is 3 ATM, so the pressure will be more. So as soon as there is a hole, like the whole gas will move out of the container. I thought, sir, I didn't know.
Understood. It makes sense, right? It makes
Yes.
logical sense also, right? Yeah. Thank you, Shruti. Thank you. Right. So obviously, no people, right? Say I have like look at this. Okay. Now I will take this case. Okay. Say you have a classroom, right? So in your classroom, say maximum I can accommodate 50 people. Okay, maximum I can accommodate 50 people. Okay, let me take two cases, right? Say first case I have 40 kids, right? I have locked them up and kept them there for 1 day without food, without nothing. I just I can make them starve, right? I'm not that bad, but still, it's just a situation. So yeah, so we are doing that, right? The second case, I have almost like 80 kids in the same classroom and same situation, no food, nothing, just lock them up, right? So when I open it, in which case people will be running out faster, obviously, right? In obviously, again, it's just a situation for you to understand, right? So obviously, in the second case where there was more pressure, in the sense there was at maximum capacity itself is 50, so more than that I had some 30 more people, right? So obviously I can say that this can be analyzed with this also. So right, so what happens? So here already the particles are moving faster, in the sense they are going and hitting the walls of the container with greater force in case of 3 ATM than 2 ATM, isn't it? So obviously what will happen now? Oh, or in other words, if at all I want to speak very technically, right? So can I say, right, this diffusion or effusion, right, actually depends on the pressure difference. What is the pressure difference between what and what? Pressure difference between the inside, that is the inside the vessel, whatever is the pressure, and to the place wherever it is moving. Now, okay, just go back to the definition. It says it is the movement of gas particles from a region of higher partial pressure to the region of lower partial pressure. How high the partial pressure, how low the outside partial pressure is matters. That means the pressure difference between these two sides, that is the high pressure side and the lower pressure side, that matters, right? Higher the difference, faster will be the movement of the gases, as in faster will be the diffusion. Correct. So obviously in this you can see, understand that it is 2 ATM inside, and obviously I know outside what will be the pressure, assuming that it is atmosphere. So I have 1 ATM outside, right? So I have a pressure difference of only 1 ATM. 2 minus 1 is 1, right? But here 3 ATM, but still the outside pressure is only 1 ATM. So the pressure difference is very high, right? So obviously, so there in the case of 3 ATM, the gases will effuse faster, right? So yeah, so definitely pressure in case of effusion plays a very major role, right? Okay, now let me ask you this way, right? Both are 2 ATM, okay, both are 2 ATM, but what I'm changing is the temperature. Say this is at 30 degrees Celsius, this is at 50 degrees Celsius. Now tell me, say case 1, case 2, where effusion will occur faster. I think this should be easier than the previous case.
Yes, too, sir.
Definitely right. Definitely right. Obviously, we saw how many equations relating to temperature, velocity, kinetic energy. In all the cases, what you saw, that particular term and temperature are directly proportional, isn't it? Right. So obviously, higher temperature means higher kinetic energy. Obviously, the more and more will be the rate of diffusion. So definitely, in case 2, you will have more rate, faster rate of diffusion, right? Cool. So what I'm trying to tell you is this is not the only what is that? This is not the only factor which decides the rate of diffusion. But for your problems, they wouldn't ask you all these things. Don't worry. They will not go into all these things, right? They will just correlate on only this molecular mass term. Okay, right? Cool. So what else I had to say? Yeah, again they can do it. Well, the maximum tough question which can be asked from here is they can do it in terms of density. That's it, right? So density, I can give you one more equation. R1 by R2 is equal to root of D2 by D1. Right? Root of D2 by D1. D2 is the density of the second gas. D1 is the density of the first gas. Right? Now, how did I directly put it? Very simple. Now, I know density is equal to mass by volume. Right? So, molecular mass, obviously, I see it's directly related. Volume kept constant. That means the volume of the vessel in both the cases, right, will be constant. Only then I'll be able to write this, obviously, right? So yeah, or I can even hope you remember one equation for density. It's equal to Pm by RT. Do you remember this?
Yes, sir.
Good. So this is an equation which we derived, right? So again, if pressure is constant, temperature is constant, density and molecular mass are directly related. So I can use this equation in terms of your density also. Cool. Now, what is the time? We'll quickly do some problems. Okay. So I have to tell you how should I calculate the rate? Like sometimes maybe they can ask you, right? What is the rate of diffusion? Other than asking the ratios of rate of diffusions, right? They might have to calculate what is the rate of diffusion, right? So that we'll see how to do it, right? Okay. Right. So yeah, so how to calculate rate? Rate is equal to, right? Del V divided by del T, where del V is the change in volume. Right? Del V is the change in volume and del T is the time period. Del T is the time period. Okay, right? So obviously you can understand, right? For example, say I have a vessel in which I have a gas and I made a small hole, right? Now what I can say obviously I can see that in 10 seconds, right? In 10 seconds, through this hole, I got like say 2 ml of the gas, right? So here I say that in 10 seconds, I outside, obviously I'm not talking about the inside, I'm talking about outside. So in 10 seconds, I saw that 2 ml of gas have diffused or effused, right? So now what is the change in volume? Change in volume in a sense, how much came out? I can keep it like, initially I can say that initially outside is 0. Sorry guys. So yeah, so initially the volume of the gas outside is 0 initially, right? But finally how much is there? 2 ml, right? So I can write it as V. So how do I write del V? Del V is V final minus V initial, right? Time period is T final minus T initial, or you can just write T, doesn't matter. Right? Del T, because generally we take the initial time period to be 0, generally, right? So I can even write T directly, right? So V final minus V initial divided by T. So now in this case, V final is 2, V initial was 0, outside, I mean, how much gas is diffused at time T is equal to 0? 0. V initial is 0. Finally, I have 2 ml of gas effused in 10 seconds. So divided by 10. So basically 10 by 2 is what? 0.2 ml per second would have been the rate of diffusion. Okay, do you understand how I calculate? Right, it is very simple formula. How much has diffused divided by how much time was taken for that. How do you say, generally say rate? When I say rate of change, when I say velocity, or what do you say? You say it is rate of change of diffusion. Sorry, rate of change of displacement, right?
Yes, sir.
Okay, so what do you do there? So displacement divided by time. That's what you do, correct? So here also talking about the rate. So definitely we have to divide that particular quantity by time, right? Here you're talking in terms of volume. You can even talk in terms of pressure if you want. It's all about it. It's all about how you calculate it, right? So I can even say that instead of saying 2 ml of the gas, I could have said that say 0.2 atm of the gas has come out. Now in that case, the volume will not be in terms of this thing. It would have been say del P divided by del T. You can use it, but I don't think that level and all they'll go, right? But even if they go, you can simply use logic and get the answer. You don't have to have very fancy formulas to know all these. These are simple mathematics and physics which you can apply, right? Okay, now we are good enough to do the problems. Okay. Second on the question. $50 ml, 50 ml of H2 gas, 50 ml, 50 ml of hydrogen gas diffuse through a small hole from a vessel. Diffuse through a small hole. Again, it's called diffuse through a small hole. I can put the entire statement in one word as effusion. Anyways, right. So 50 ml of H2 gas diffuse through a small hole from a vessel. In 20 minutes, 20 minutes. Right? So now the question is, calculate the time taken by 40 ml, 40 ml of time taken by 40 ml, 40 ml of O2 gas to diffuse under similar conditions.
Sir, can you repeat the question?
Yeah, sure. Right. So I'll repeat the question now. I'm telling 50 ml of H2 gas diffused through a small hole from a vessel in 20 minutes. Right. So 50 ml of hydrogen gas diffuses through a hole in 20 minutes. They're asking calculate the time taken by 40 ml. Right. So I have 40 ml of O2 gas. Find the time taken by 40 ml of O2 gas to diffuse under similar conditions. What do you mean by similar conditions? Same temperature, same pressure, same size of the hole. Like other than the volume of the gas diffused and the gas itself. First case is hydrogen gas. Second case it is oxygen gas. First case it is 50 ml. Second case it is 40 ml. Right? Asking you what is the time taken by O2 gas for this many ml to get diffused. I'll give you 3 minutes. Okay, go for it. I want the answer in minutes only. You don't have to convert it to seconds. Just tell me the answer. We'll see if anybody gets the answer. So you have to use two equations. One is Graham's law, right? Second one is this.
Sir,
Yeah.
is it 64 minutes?
I guess it should. I'm not sure, but yeah, options are there. It's actually MCQ. I'm not giving you the options. Yeah, 64 minutes option is there. It might be a correct answer. We'll check. There is one more minute. If anybody wants to give an answer, you have one more minute. Right? So I think time's up. I'll do it. Right. So here they're talking about hydrogen gas and oxygen gas. So if I use Graham's law, right, this is how it's going to look. R of H2 divided by R of O2, rate of diffusion of H2 divided by rate of diffusion of O2 will be equal to molecular mass of O2 divided by molecular mass of H2. Yes, R1 by R2 is equal to root of M2 by M1. Yes, O2 by H2, here H2 by O2. Done. So now I can just directly use my rate. I can calculate the rate directly here using my del V by T, right? Del right. R is equal to del V divided by T, change in volume divided by time, right? Okay. So now what they're telling? They're telling that 50 ml of hydrogen gas. So they're telling that, okay, 50 ml of hydrogen gas in how many seconds? In 20 minutes, right? This is my rate of H2, right? Divided by, or I'll not do like this, 1 second. So I can calculate rate of H2 will be equal to del V divided by T, which will be 50 divided by 20, 50 ml divided by 20 minutes, right? Now rate of O2, I don't know because I don't know the time period, but they have given the volume. Volume is 20 divided by T, some T. I don't know, whatever it is, right? Now these two are the rates. Let me plug it here. So I have 50 divided by 20, and if I bring this out, it will become T divided by 40, right? It will be 40 divided by T. If I take it up, which will be equal to root of molecular mass of O2. Molecular mass of O2 is 32, right? Right. And molecular mass of H2 is 2. Okay, right? So this will become 16. So root of 16 will become 4, right? So what I'm left with? I'm basically left with this is equal to this. So if I bring T is equal to 4 into 40 divided by into 20 divided by 50, 8 times. Okay, so 8 into 2 is 16, 16 into 4 is 64. Your answer is correct. Yeah, the answer is 64 minutes. Any questions? Anybody did not understand what I did here? Please tell me. Everybody understood?
Yes, sir.
Others?
Yes, sir.
Yes, sir.
Okay. Okay. Pranav, did you understand? Pranav? Is he there? Pranav is there. Okay, he's texting something. What happened? Okay, fine, cool. Right, fine. So do not think like why out of nowhere I just asked Pranav. It was random because nobody else was answering. Right, okay, fine. So one more question. Find the ratio. Okay, if you want time to take this down, I'll give you 1 more minute. Then I'll give this. Okay, now the question. This is a relatively easier question than previous case. Right. Okay. So they're asking, find the ratio of a rate of diffusion. Find the ratio of rate of diffusions of helium to methane. Helium to methane. Obviously, all the conditions are same, temperature, pressure, all the size of the hole or whatever it is, they are same, right? So they're asking find the ratio of diffusions of helium to methane. That's the question. Go for it. So this question was asked in IIT JEE 2005. So if you can actually just look at our history, we have actually solved only tough problems, right? And the motive is not to make you feel say not to lower your confidence, right? If at all you solve it, anyways I'm going to teach you, right? So if at all you know the toughest of problems, easy problems, anyways you'll be able to do, right? So that's the point. You prepare for the worst, and obviously the best will happen to you. Yeah, but this question is very easy. You just have to use one equation.
Two is to 1, sir.
Yeah, right. So very simple. I just have to use this equation, except that it is not going to be O2 and H2. Here it is going to be helium and methane. I forgot to ask, how was the test periodic table?
I
Right?
had a doubt.
Okay. First we'll finish this question, then we'll come back to that. Okay.
Yes, sir.
Right. So I have helium and I have CH4. Rate of helium by rate of CH4 should be equal to root of molecular mass of CH4 divided by molecular mass of or molar mass of helium. Right. So they're asking this ratio only. This is what we have to find. So it's root of CH4 is 16, 12 plus 4 is 16, helium is 4, right? So it will be root of 4, which is 2. So yeah, the ratio is 2 is to 1. Very, very simple. Just a simple formula substitution. Right. So yeah, tell me, what was the doubt?
What is this long form of periodic table means the modern periodic table, sir?
Yes. That's long
Can
form.
you iterate what is no actually what are the advantages, sir?
Oh, so basically they're asking you to compare Mendeleev's and the long form, right?
Oh,
The question
Obviously,
was just about The advantages of long form of periodic table, sir.
Table, yes, sir.
Yes. Okay, you can write with respect to the previous things you have learned, right? Obviously, isotopes was a problem, right? If at all, because in Mendeleev's or on all the other periodic tables before, right? What is the periodic function? Periodic function was basically atomic mass, right? Long form of periodic table is the first time people are using atomic numbers as the periodic function. So definitely the problem of isotopes is not going to be there. If at all, if you only use atomic mass, for hydrogen, deuterium, and tritium, I have to give 3 different places in the periodic table, right? But here, that thing is taken care. And what else? Like advantage, you can even tell that even for the elements which are going to be discovered, we have places, right, left for them. UUD, UUN, UMB, all these things, they say, right? And what else? What are the other? It is easy to classify, right? So there is no distinguishing. Basically, the elements in the same group, almost all the times, right? They actually have similar chemical properties. It is way easier to study long form of periodic table than the other forms of periodic table. So yeah, these are all some of the advantages of long form of periodic table. Right? Any other question you had? Doubt?
Yes, sir, but it's not from the test.
No
Generally.
problem. Tell me.
Sir, like how do you find the group and period numbers, sir, of an element? I mean, for 118 plus, I know, sir, like 119120.
Easy, right? I told you to remember
under
these magic numbers. I'll again help you. You spend some good enough time on this. If I give you the atomic number, right, how will you find the period number? Or period number as well as the group number, obviously, right? Okay, so for that, you need to remember some magic numbers. So magic numbers in the sense, you have to remember what is the atomic numbers of all the noble gases. If you can remember that, yes, it makes it easy. So I know helium, 2, helium, neon, argon, xenon, krypton. Okay, I think the last one is oganesium. I'm not sure. Okay, so 2, 8, 18. I think it's 54, 86. Last one plus. You just add plus 36. Plus 36 will become 122. 36 or 32? 32 only. 32, if I make it, it's going to become 118. Okay, right. So yeah, these are the numbers which you have to remember. Now, you can easily remember it. Oh, this is not 8. This is 10.
10, sir.
10, right? So for this, the difference would be 8, right? For all this, the difference would be 32. Is it? Am I missing something? Helium, neon,
yes, sir.
argon.
After argon, you missed one element.
Exactly. What is that?
I think
Helium, neon,
krypton is
argon.
36.
Krypton is 36. Okay, xenon. Oh, radon. Okay. Yeah, I missed one. Correct. I missed something. So here, before xenon, I should have krypton, which is 36. Then comes your radon, which is 80 plus 32, would be 86. Yeah. Right. So remember, for the first 3, right? For the first 3, it is the difference would be 8. For these 2, the difference would be 18. Correct. And for all the other 3, the difference would be 32. Right. So this you remember. Okay. So anyways, so if you can remember the what is that? The atomic numbers, right? Say I'll take a random. You give me some random number. We'll do it.
74, sir.
74. Okay. Right. So now first you have to look at 74 comes between which 2 numbers, right? So here I can see that it is coming between 54 and 86, right? So please understand, this is my first period, helium and hydrogen. second period, third period, fourth period, fifth period, sixth period, and seventh period. Right? So where is it coming between? It is coming between xenon and radon. So definitely it is going to be in the sixth period before this, right? Okay. Now we know you're told 74, right?
Yes, sir.
74. Now 74. Now look at this. I have 86 as the last. Last member in this period, which is having 86, right? And you're giving me 74. So can I say the difference is 12? Right? Difference is 12, and you can see I basically have 18 groups. Please remember that I have 18 groups in this. Correct, right? Or you can say it like this. You can count backwards, right? You can count backwards 12 groups like this, because the before this would be 85, 84, 83, 82, 81, like that. It is going to reach 74 in this period, right? Or you can start from the other one. Now 54 ends here. Now the next group 1 would have had 55, then 56. Group 2 will have 56. Like that, I'll be able to calculate it. Now I'll be able to tell you the answer now. So now this is now remember that this is group 18, right? Now what is the difference? Difference is 12, right? So obviously, if I minus 12, what is coming? 6.
6.
So this element belongs to group 6 and period 6.
Okay, so understood.
I think everybody is a good method by which you can do. Right. So remember the numbers. First, find out the period number, because you can easily say between two atomic numbers, it is going to stay. So you can say which period it is for sure. And after knowing the period number, look at the atomic number. Look at the last group elements' atomic number. Minus them. Right. The number which you're going to get is the group number. Okay. Fine. Any other doubts? Anybody has?
Sir, if we know the electronic configuration only, we can just find these group and period or the particular element.
Yeah, wonderful. That is actually a good method, right? You can write the electronic configuration for 74, right? And obviously you know what is the general electronic configuration for all the periods. Sorry, all the groups. For example, group 1, right, will have NS1. Group 2 will have, we're talking about valence electron configuration, right? So group 2 will have NS2. Like that, say group 13 will have NS2 NT1. So yeah, that also is a good way. But what happens is, if at all the element is going to be in the S block or P block, no problem, right? But if the element is going to be in like say D and F block, in the inner trans, the middle elements, the middle groups, there sometimes the electronic configuration will not help you find the period number and group number. But yeah, 90% of times it will help you, right? But yeah, sometimes it might go wrong, because you know, especially in F block elements, right? So if you look at the configurations, the valence electronic configuration is not what you expect. It is little different. That's the reason. Even in some of the D block elements, right? You will get to know more about this when I go for 12th class. D and F block elements, I have a separate chapter. At that time, we'll see.
Yeah. Okay, sir.
But yeah, definitely a good way. Definitely a good way to write the electronic configuration and check. Yes. Right. Yeah. So any other question?
Sir, and there's a question. Give the properties of the oxides in a particular period.
Okay. What period? Period of
Yes, sir. Given particular period.
Maybe they're asking you. Are they asking you to compare the properties of oxides in a period?
It's just given like that.
Okay. Maybe that's what. Maybe they're asking you to compare in a period. I have some elements, right? What happens to the properties of oxygen? Properties of oxides of these elements.
Sir, I just wrote that on the left-hand side of the period it's metallic, basic oxides.
Yeah,
so
sir,
on
metallic
right-hand
oxide.
side it's acidic
Exactly.
oxides.
You
Acidic
mentioned metallic oxides. Metallic oxides are basic. Non-metallic oxides are acidic. This much you mentioned. Yes, I'll give you marks. Yeah.
Then I had a doubt, and this should we mention about amphoteric oxides also? Neutral oxides, amphoteric oxides.
I wrote
Since we
Not
are in the
exactly.
middle.
Because if you have mentioned it, very good, but it is not necessary in this question. If you just mention that
Okay,
the
sir.
basic character or the acidic character decreases or increases from left to right of the period, yes, it is enough.
Okay, sir.
Right? Okay. Any other question? Not regarding this chapter, some other chapter, some other question, somewhere you saw.
Sir, from that Schrodinger wave equation, how will they ask question from it, sir?
They will not ask you questions. Don't worry. Right.
Yeah, okay, sir.
Schrodinger wave equation, they will not ask you. But they will definitely ask you questions from quantum numbers, for sure.
Yeah, okay, sir.
Okay. Right? Yeah. Any other questions? Okay. So I assume that all your questions are answered. And people,
I'll
so I
ask
think
next class, sir. And
right,
I'll
you
ask
can
my
ask.
doubts next class, sir. No, sir,
Right, sir.
I did not take down the questions, sir. So I'll take down and ask you next class.
Okay, cool. No problem, no problem. Right. So yeah, and regarding what is the day today? It is Friday. Okay. Guys, next Saturday. Next Saturday, will it be fine? Okay. Next Saturday, right? We are going to have a test on chemical bonding. Okay, but not the entire chapter, right? So we will keep Lewis theory and valence bond theory. Valence bond theory, that is excluding hybridization. Like with what to say, Lewis concept we know, right? Then I'm going for VBT. VBT, you know, it's about the overlaps, right? Different types of overlaps, sigma bond, pi bond, right? Ionic bonds, all these things are there, right? So ionic bonds, Lewis theory and valence bond theory. These three will be the portions for your test on next weekend. I'll confirm the dates, okay? But you can start preparing, right? Okay. But actually, fine. Anyways, we'll go with this. Cool.
Lewis
Right. So
theory,
next,
valence bond, and
ionic bonds. Ionic bonds, not the covalent character ionic bonds, not that. Only ionic bonds. General questions can come. Okay. Right. So yeah, these three topics, because it's a very little big chapter, I thought I will cut it down. Right. Okay. So yeah, these are all the things you have to know. Okay. Thank you guys. I think I took so much of your time. Right? You can go to your school classes. Right? Thank you so much. Bye bye.
thank you, sir.
Thank you.
Thank you, sir.
You.